I am R.P. Luthra on behalf of IIChE NRC. I welcome all the guests in our Learning with Leaders program, which is our flagship program and being conducted every month by inviting speakers with great knowledge and experience. And so far, in the last 10 years, we have conducted more than 60 such programs by inviting highly eminent speakers, and which has been very much enjoyed by our all participants. Today, we are having a lecture by Mr. Ajay Popat on MBR, which is I hope is a very interesting subject, and it will be enjoyed by all the speakers. Now, I would request our Honorary Secretary, Mr. C.P. Srivastava, to give a welcome address and introduction of the speaker.
Thank you, Luthra Saab. I take this opportunity to welcome you all for this lecture program by Mr. Ajay Popat as a part of the NRC activities. So a special welcome to the speaker, Mr. Ajay Popat.
Thank you very much. Good morning, everyone.
Yeah, to the participants and to all the persons associated. Although the brief profile of Mr. Popat has been circulated along with the notice for the lecture, but still I take this opportunity to give a very, very brief introduction. Mr. Ajay Popat, who is presently the president in Ion Exchange India Limited, a very renowned company in the ion exchange technology, is a engineering graduate in plastic technology, MBA in marketing and strategy, and a fellow of Indian Plastic Institute. He is also associated with a number of trade and industry organizations like CII, IIChE, SOChem, Water Quality Association, PPMAI, etc., and actively working in the field of environmental management, water purification, wastewater management, etc. In fact, while in Ion Exchange India, he was also responsible for launching a joint venture company for the purpose of environment management business, for which he held the position of a CEO and led that company to work in that area. So with more than 40 years of experience in this field of water treatment, wastewater management, or wastewater treatment, and purification, and moreover, development of sustainable technologies in these areas. Papers published by him, sharing his knowledge with others. Now I request Mr. Popat to please start his lecture with a very, very important of membrane bioreactors technology. So far we have been, associated and listening and working with the membranes as a separation process. But now let's have some awareness and glimpse of how the membranes are going to working in the bioreactors technology. So once again, welcoming Mr. Popat, we request you to please proceed. Thank you.
Thank you very much, Mr. Srivastav. And can you see my slides, please?
Yeah.
Yes.
Okay. So once again, very warm welcome to members of Indian Institute of Chemical Engineering, Northern Region. Also, a big thanks to IIChE North Region organizers, Mr. Bang, Mr. Luthra, Mr. Srivastav, for inviting me this morning to share knowledge on the concept of membrane bioreactor. So I'll now start my presentation, and generally before I begin my presentation, I always ask the audience, saying that I have tried to possibly cover most of the subjects for which you are present here to learn more about. So while doing that, it is possible that some topics, and we have got a cross section of people, somebody who's familiar, somebody who's just trying to understand. Maybe there are some students here, and someone who's an expert on the subject of MBR after applying the technology commercially. So we've got a cross section of people, and obviously each person would be here to understand from his or her perspective. So while I have made an attempt to cover all aspects of MBR technology, my suggestion and request is that we keep the question and answers at the end of my presentation, because I'm sure I've made an attempt to cover everything, almost everything. And in case if there is something left out, we could always discuss during the question and the answer session. Is this acceptable, Mr. Luthra, to everybody? And also Mr. Srivastav, is this acceptable?
Yeah, it's fine.
This is a good idea.
Yeah, because I want to make this very, very informal. Okay, though I may be dressed formally because I have to, but I love satsangs, and I love this sort of interactions which are a bit more informal. Because the whole idea is to exchange knowledge and information, and but there has to be certain amount of structure in order to see that the program goes on well. So thank you for your consent. Very quickly, let me begin. Not more than about 4 slides about my company. Our vision is to be leader in our business, which is so vital to people's lives and environment. And this is a vision which drives us towards all our objectives, be it with respect to business, social, or corporates. Over the 5 decades of expertise, we were born in 1964 and we have a British parenthood, because in 64, when we were born, it was the British permutate, and all of you know permutate then and even now in the textbooks, it's a very renowned name. So since then, we have more than 100,000 installations for water, waste treatment, process treatment, and recovery globally. Of this, 1,000 installations are in core sectors like thermal power plants, nuclear power stations, fertilizer factories, refineries, and petrochemical. My company exports nearly 45% of our revenue. My company's revenue is close to about 1,500 crores, of which nearly 45% is exported to America, Europe, Southeast Asia, Middle East, and Africa. We have an extensive infrastructure. I'll talk more about it in terms of manufacturing, service, very importantly, global presence, and production facilities. So this is something about very quickly about my company. I explained our revenue is about 1,500 crores. Of this 1,500 crores, 56% comes from engineering, providing customized as well as standardized water, waste treatment, process separation solutions. 35% is chemicals, which includes ion exchange resins, water treatment chemicals, process chemicals used by various industries, and about 9% is consumer products under the brand name of Zero B. For the last year is March 21, our EBITDA was close to about 202 crores. We focus on industries, institutions, international business, and also now to municipal applications. And our profit after tax was about 143 crores. We are a publicly listed company. since early 80s, and since the time we have been listed on major bourses, we have an uninterrupted dividend paying record to our shareholders. These are our manufacturing facilities in Ankleshwar, Gujarat. We make world-class ion exchange resins. We have a 50% market share in India, and nearly 45% of the production is exported, mainly to Americas. So that shows our ability to compete by making it India and transporting resins all the way to America, where there are existing manufacturers, and also we compete with China, but we are highly successful in these areas. This facility also has pharmaceutical grade resin manufacturing. So we make excipients which are used for taste masking, sustained release. They are used for kidney dialysis. They are used for directly into as a drug product, like for example for cholesterol reduction. Our resins are used very successfully. They substitute the statin, which had so many side effects. So we have the regular industrial production and a state-of-art pharma facility here to make this FDA compliant ion exchange resin used as excipient. In Patancheru, Hyderabad, we make a range of polymers, mainly for water treatment chemicals. We make antiscalants, we make polyelectrolytes, coagulants, flocculants, and also a wide variety of process chemicals, which are used for textiles, upstream and downstream petrochemicals, for paper industry, etc. We do have a fabrication facility in Hosur, near Bangalore, but technically in Tamil Nadu. So every time we develop water or waste treatment design, we standardize it. So it's just like buying a television which fits your room size or your choice. So it's like a plug and play system in terms of water waste treatment. So these are prefabricated, pre-designed system where you don't have to spend time on engineering and use standard components in order to effect quick deliveries and also at a very competitive price. We have our Center of Membrane Excellence, the topic why we all are gathered here, one of the topics why we are gathered here in Goa. So we are the only manufacturers of membranes in India in a state-of-art manufacturing facility, which was inaugurated 3 years back. And I'm very happy to say that within these 3 years, we now have a dominant market share for membranes in India and increasing exports to several countries. Very close to the membrane manufacturing factory, about 10 kilometers, is an assembly center where we convert these membranes into MBR systems, RO systems, ultrafiltration systems, nanofiltration systems, etc. So Goa is the center of membrane excellence. Maybe IIChE, when the time is good, which is now, or probably sometimes, could organize a visit for its members, because nobody will show you a membrane manufacturing facility. We'll be proud to show you how membranes are manufactured in our factory. Some of the pictures are over here. All our manufacturing facilities are ISO 9000 certified. The pharma facilities in Hosur, because in Hosur we also make high purity water systems, which have to comply to the exacting USP norms. So like in Ankleshwar, where we make resins, here we make water treatment equipments required by the pharma and the high purity industry. So those are FDA approved. And otherwise everything is ISO 9000 approved. All the chemical factories are ISO 14000 certified for environment quality management systems. These are our other fabrication facilities in Wada, Maharashtra, where we make FRP vessels. We do stainless steel fabrications. And very close to Mumbai and Rabale, we have our export-oriented unit from where we export our water and waste treatment plants. Outside India, we have manufacturing facilities in Middle East, in Hamaria Free Trade Zone. We have a chemical and equipment assembly center in Bahrain. We have a center in Indonesia to cater to Southeast Asia. As you could see, this is to meet the local requirements with standard systems of water and waste treatment as well as chemicals, strategically located in geographies from where we get 45% of our revenue through exports. We have a strong focus on research and development with a well-established in-house R&D department 1 year after we were born in 1965. So this is recognized by Department of Science, Scientific and Industrial Research for chemicals at Patancheru, and for engineering products in Vashi, Navi Mumbai. So we have product application and testing centers with numerous patents to our credit, more than 50 patents, out of which we have commercialized about 100 products. Our design centers for MBRs, water treatment, waste treatment, zero liquid discharge are located in Rabale, Navi Mumbai, Vashi, in Kolkata, as well as in Hosur, Tamil Nadu. So we have a strength of about 300 people working in these design centers using advanced tools for designing of the plants. Here is a view of 3D modeling of waste treatment facility that we have. And this is we do for all our jobs. So there's a walk-in that we do for all the contracts that we receive in order to ensure that there are no gaps in our engineering design and at the time when we go for construction. We are the largest service providers with more than about 14,000 industrial customers whose water and waste treatment plants are operated and maintained by us. Also qualifying largest is that we employ 3,500 people only in services to service the requirement of these 14,000 customers. And our comprehensive range includes water management surveys, rehabilitation, retrofit of existing plants, of course, erection and commissioning. We do a lot of build on operate projects using our own technology, our own investment, and also our own staff to operate and maintain those plants. We do a lot of operator trainings and very importantly, supply of genuine spares and consumables to these 14,000 customers located all over India. And these are only industrial customers. I have not included home water, domestic, which would be almost about 1 lakh customers. We have a strong emphasis on EHSS through a well-documented EHSS management system, compliance, operational control, best practices and training as a part of our EHSS program. And this is our certification on EMS, OHSMS, as well as the QMS systems. So against that background about my company, to the subject proper, why we all are here on membrane bioreactor. Let me take you through a bit of a concept about, I'm sorry, I moved the slide, on the concept of now, all of us know that there are various types of biological processes. Okay, so what do these biological processes do is they treat effluents which contain primarily organic matters, because here we are now talking of biological processes. So I'm excluding the pre-treatment which is used generally, which is required generally for biological treatment of waste. In order to remove that is generally done through physicochemical treatment process. So once you remove suspended solids, once you remove oil and grease, you neutralize the effluent to a pH which is right for biologically treating it. You then go to the biological process. So pre-treatment is very, very important for the design as well as for the performance of biological process plants. Here we'll assume that the effluent is pre-treated and just contains only the organic matters. And of course, there will be something like TDS, which will be present even after the pre-treatment, because TDS is removed post-biological process in membrane systems. So this is an effluent containing organic matter. We have two options to treat it biologically. One is in presence of oxygen, what we call as an aerobic process or an activated sludge process, in which the organic matter is destructed into carbon dioxide, water, and new bacteria. In absence of oxygen, one can also destruct organically contaminated effluents through an anaerobic process. And in anaerobic digestion, one produces methane or biogas, water, and also the new bacteria. So these are fundamentally the two biological processes. Our topic today is mainly with aerobic process. Within aerobic process, there are various processes like attached growth process as well as activated sludge process. Today, we are going to talk about the activated sludge process and not essentially about attached growth process, because when you talk of MBR, the aerobic biological process follows the fundamental activated sludge process in its design. So it's a suspended growth process. It needs favorable condition for growth and separation of biomass from the water. This is very important because that is where the membranes come into the picture. The biological solids are used over and over. What I mean is that they are recirculated. The new biomass is wasted in case if it exceeds certain volumes or certain quantity, but it is generally reused again and again. And you have feed and bleed type of a system that once you have the right volume of biomass in your reactor, whatever is excess is then bled and it is dewatered or it is stored for subsequent uses. And the growth rate produces about 0.7 kgs of biological solids per kg of BOD removed. These are certain thumb rules which are very important also for the design of downstream dewatering equipment. But these are some fundamental figures in order to design a good aerobic process. Now, if you look at the whole design here as how we go about designing aerobic processes. What are the parameters? The parameters are obviously organic load. We should know what is the BOD COD. We should also know what are the BOD COD associated with, let's say, ammonical nitrogen, or is there an organic phosphorus present? So we need to know everything about the organic load, quantified generally as BOD, COD, ammonia, phosphorus, etc., etc. So once we know the organic load, we also design the system based on F to M ratio. F is food and M is the biomass. I'll talk more about it. Then we need to have the right biomass quantity. As I said earlier, like for example, if it's an activated sludge process, we say that the MLSS should be about 2,000 to 3,000 or 4,000 milligram per liter. If it's an variation of an activated sludge process, which is an MBR, we talk of MLS is as high as up to about 8,000 to up to about 12,000. So the biomass, its quantity and age is very important for the design. Then of course, it's an aerobic process. So we should have right amount of dissolved oxygen. And that's what is called as DO. So it's a parameter for design as well as for control. Then of course, the hydraulic load with which a reactor is designed, and what is also the solid load. So typically called as hydraulic retention time or solid retention time. And finally, post clarifier designed rightly to ensure that the excess biomass which overflows from a bioreactor or an aerobic reactor settles properly. And then it is, as I said, used over and over again through a recirculation. So also the recirculation pumps are accordingly designed to maintain a steady state of biomass volume in the aeration reactor, and then also wasting the excess biomass which is produced. So things like sludge blanket depth and the settability of the biomass, aided by the right coagulants and the flocculants to have an optimum design. The reacted activated sludge, the waste activated sludge lines. So these are the design basis. Now let's look at what is a membrane bioreactor. It combines the conventional biological treatment process or the activated sludge, which I just described in the previous slide, with a membrane filtration to provide an advanced level of organic and suspended solids removal. Please mark my word that, and I always say that while matter is neither created nor destroyed, the same way I also say that the sun would generally rise in the east and will set in the west. And the variations and the innovations will see that depending upon the country where you are, maybe in Japan it rises early, and maybe when it comes to India it rises a little bit late. Maybe during winter and during summer it changes its angle. But these are the only variations that you could do with the rising and the setting of the sun. This also applies for most processes. So if someone comes and tells you that he has got something fantastic in terms of MBR, just please understand that it is nothing but an activated sludge process, improvised in order to have a better level of organic reduction and the suspended solids removal. So as you see here that the influent, the pre-treated influent enters the MBR system, And unlike an activated sludge process, which is having a load of about 2,000 to 4,000 of biomass, here, as I said, you can go up to about 8,000 to 12,000 milligram per liter. So it's a high rate biological treatment. From here, it goes to a membrane, which is immersed, or it could be MBRs are different types. You can have an immersed MBR, or you can have a side stream MBR. I'll come about types of MBR very soon. But for the moment, understand these are two separate process units. In reality, they are integrated in an aeration tank, or maybe if it's external MBR, it is outside the aeration tank. Most of the time, you'll have two tanks. You'll have a bioreactor tank and you'll have an MBR tank. So what this MBR membrane does is essentially filtration of your biomass, something which was done in an activated sludge process, a conventional activated sludge process, through a clarifier. So essentially the membrane does the job of a clarifier, but it does it more efficiently because it concentrates more and it brings more amount of biomass back to the aerobic reactor. So the design of the conventional activated sludge process was restricted by the inability of a clarifier to be designed beyond 2000 or 4000 ppm. It was not that the activated sludge process cannot be designed for 8000 or 12,000, but the limitation was the clarifier, which returned back the sludge, or otherwise, the sludge would also overflow in case if it is beyond 3000 and 4000. So you'll have more overflow coming, and then you'll have that being reported as excess BOD and COD because of the presence of the biomass, which the clarifier cannot settle even with coagulants and flocculants added to it. So the membrane does a very efficient separation and concentration, bringing it back. So this, as you will now realize, is no different than an activated sludge process, but it is now more efficient in terms of the biomass concentration and its ability thereby to reduce the COD, BOD, or the destructible organics to a great extent. So it's a positive filter with high degree of biomass solid control, consistently high effluent quality, and lower operator attentions and the compact. And now when you have more MLSS, obviously you have large capacity throughput, you have more compact footprint, and it's also more reliable as a process. And this is what actually the membrane does. This is the membrane. It offers a barrier. So it retains the biomass, concentrating it up to about 8,000 to 12,000. And the membrane will allow only the clean water and some amount of solids whose size is lower than the cutoff size of the membrane to pass through. So essentially, it combines an activated sludge process with membrane filtration to do the biological degradation. What are the advantages? You will get consistent treated water quality with complete disinfection. In a typical activated sludge process, post-biological process, activated sludge clarification, one has to do disinfection with chlorine or oxidants, etc. Here, the membrane itself is a good barrier to microorganisms. So typically, you will have 6 log reduction of bacteria, 4 log reduction of viruses, and 2 log reductions of cysts. So you don't have to do any chemical treatment to destruct, and you get complete disinfection. And the highest removal rate of COD, BOD, and ammonical nitrogen. Competitive life cycle cost. I'll talk what is the life cycle cost at almost the end of my slide. It's basically integrating the cost of capital plus the operating cost over the life of the asset and also the operating cost. And lower operating costs due to lower power in chemical consumption, because the membranes which are used here are low pressure membranes, unlike ROs or NF, which are high pressure membranes. So the cost of filtration is far lower, and overall you will have a much lower cost of electricity and of course chemicals. Lower sludge production because of increased sludge retention time. Typically the sludge retention time is 25 days, 20 to 25 days, unlike an activated sludge process which is designed for about 10 to 15 days. So higher sludge retention, higher MLSS concentration, lower sludge production, and thereby reducing the downside sludge treatment facilities in terms of size as well as the cost. And these plants by default are fully automated. So if someone comes and says my MBR is automated, he cannot operate an MBR unless it's automated. So it's a given thing. But marketeers often use this to sell it as a USP. So by default, it's a fully automated system. low fouling and backwashable of membrane. This is all done automatically with less cleaning and combustion. That's the advantage of automation. It's a stable operation working at extremely low transmembrane pressures. I'll talk more about TMP in my subsequent slides. Less cleaning frequency and obviously the high membrane life. Typically membrane life, if a good operated plant, is between 3 to 5 years. Now, if you look at the design parameters and its advantage over conventional activated sludge processes. So the sludge retention for an ASP is about 5 to 15. Here it's more than about 20. MLSS, as I said, is between 2,000 to 4,000. Here it's between 8,000 to 12,000. Hence, aeration tank footprint with MBR will be half of the area of the MBR system required. Now, in a conventional biological treatment, the biological process includes filtration, disinfection, apart from biological process, in 3 stages. There is 5 times the sludge production. The sludge may require some more treatment, and the sludge concentration is less than 0.8%, results in more sludge volumes. No control of sludge settability, particularly in the clarifier, which had a limitation, as I said, that you cannot have more than about 2,000 to 3,000 ppm, whereas in an MBR we learned that you can go up to about 12,000 also. No control of sludge settability. That is why you see most of the biological process, you have sludge bulking that is happening, because the controls of the aeration systems are not effectively maintained, and it results in overflow, and as a result, both sludge bulking happening in the aeration tank as well also in the clarifiers, which results into water which is contaminated and with high BOD COD values reported. Now, as against that, the MBR, the biological process, filtration and disinfection all happens in one stage. Less sludge, as we discussed, more stable sludge, and it's easy to dispose it. The sludge concentration, as you could see, is almost 100% more. It's up to about 1.5 to 2%, thereby reducing the sludge volumes, and the equipment size and the cost to treat sludge is robust, and it's a flexible design. High treatment efficiency with extremely low footprint. So these are the merits of an MBR as compared to a conventional biological process. We talked about quality of water. As you can see, that MBR produces far superior quality of water with respect to organics. BOD less than 2, COD less than 30, suspended solid less than 5 ppm, ammonical nitrogen typically less than 10 and 3 ppm. But if you add chemical post MBR, you can get these values, total nitrogen of less than 1 ppm and total phosphorus less than 0.2 ppm. So with post treatment, this is definitely possible. So sometimes MBR guys will come and quote to you this value, saying that, you know, with my MBR, my total nitrogen is less than 1 ppm, my total phosphorus is less than 0.2 ppm. Please ask him, is it with your MBR or is it along with the chemical treatment systems? Mostly it is with chemical treatment systems. So these values that I'm giving are strict comparison of MBR and ASP, because even in ASP, you can reduce nitrogen and phosphorus. You can also reduce the BOD and COD by additional post-treatment. BOD COD reduction by oxidation, and once again, nitrogen and phosphorus by adding ferric chloride and other things to reduce it below. So it is the sun, both of them are sun, except this one is a bit more better because of the advantages that we mentioned. The use of MBR is to achieve consistent treated water quality, to retrofit MBR in existing conventional activated system. So every technology has a place. There is no common panacea. You cannot say that MBR I'll apply everywhere, because you have an option. You have an option between anaerobic and aerobic. Within aerobic, you have an option between attached growth process like MBBR, for example, or you have an activated sludge process, conventional or an MBR. So each technology has a place, and its choice depends upon your exact requirements. Now, where does MBR fit is here, that if you want consistently treated water quality so that the tertiary UFRO systems work very well, maybe MBR is a good choice. But the same thing also happened with an activated sludge process. To retrofit MBR in conventional activated sludge systems, because if you are retrofitting your existing aerobic plant, you don't have enough area, and you still want better quality coming out as per the PCB norm or your own norm with respect to improved water quality, MBR is the right thing, because it is having a very compact footprint and it is more efficient in terms of its treatment. So retrofitting existingly non-functional, poor functional, or improved efficiency requirement is done very well with an MBR. It eliminates additional tertiary treatment units for disinfection as well as for subsequent BOD, COD reduction. Produces high quality of effluent, very good for treating your downstream UFRO or a new UFRO, and to achieve high volumetric load and to achieve high rate of degradation. So this is where MBR fits very well, as I have explained. Some of the concepts which are used for the design of MBR, I talked about transmembrane pressure. So we all are aware about transmembrane pressure whenever we are using ultrafiltration and RO membranes, essentially to reduce TDS and to recover water. So in case of MBR, it's the driving force of separation, which is the pressure difference between the feed side and the permeate side. And so we maintain a transmembrane pressure of very low transmembrane pressure of less than about 0.5 bar, actually about 0.2 bar or even 0.1 bar. So that's why, as I was saying, MBRs, the energy profile is very, very low. We have to maintain specific flux. Flux is nothing but, amount of water fed through a unit surface area of membrane. So it's gallons of water per square feet or liters of water per meter square hour. So this is very important design factor. So we have a very specific flux rate depending upon the type of effluents you want to treat. For sewage, it will be different. For industrial effluent, it will be different. Again, depending upon type of industrial effluent, the flux rates are different. Then there is a very important design factor called as permeability, which talks about a ratio of the gross flux and the transmembrane pressure. So we have correlated the above two parameter to have permeability factor and is directly dependent on the condition of membrane and filtration attributes of the fluid that should be permeated. So these are very important ratios and factors both at a design as well as a control stage. Now, this is a typical design guideline. For an aeration tank design for for an MBR. So MLS is typically between 5,000 to 10,000. MLVSS, the volatile component of the MLSS should be at least 75 to 80%. F by M ratio between 0.15 and 0.18. Sludge retention time 21 days. Yield coefficients, which are standard coefficients for the overall design in terms of tank volumes, the sizing, etc., is typically about 0.5 and 0.06. Not much too different than activated sludge processes. What's different here, as you would have realized now, is MLSS, which is you can go up to 12,000 as against 2,000 to 3,000 in an activated sludge process. F by M ratio, which is typically 0.1 or 0.12, you can go up to about 0.2. Sludge retention, which is 15, you can go up to 21. And the design guideline typically for MBR, as I said before, that if you're treating sewage, the flux rate is anywhere between 20 to 40 LMH. Generally, we design it at about 25 for a type of membrane. For a B type of membrane, we design it up to about 40 LMH. The operating net flux is between 10 to 20 LMH, and the air demand per module is between 16 to 48 NMQ per module. Now, there are different types of MBRs. Having understood so far the concept of MBR, its salient features and differences against activated sludge processes, where it can be applied, what are its standard design conditions, both for designing a good plant and operating it very well. Now let's look at what are the options that we have within MBR. So we have immersed or submerged MBR. These are again available as flat sheets and also as hollow fibers. Then there is also side stream, where the MBR modules are placed outside the aeration tank and with multi-tube or multi-channel membrane modules. So you have tremendous amount of permutations and combinations and choices. So here again, depending upon one specific effluent and requirement, one decides whether you will use immerse or submerge or side stream, whether you will use flat sheet or hollow fiber or multi-tube or channel. Now, in my next slide, I'll talk to you about how does one select one of these modules and what are the advantages of each of these modules. Now, let's look at submerged hollow fiber MBR. As I said, this is available in configurations of hollow fiber as well as flat sheet. Let's talk of hollow fiber first. The typical MOC is PVDF, but PES also is available, but more and more now PVDF has started replacing polyether sulfone. The pore size is typically 0.03 microns. So it's in the ultrafiltration range. It has a higher packing density and hence lower footprint as compared to flat sheet MBRs. Low air requirement, backflushable membranes or backwashable membranes. These are typically used for large flow rate industrial and municipal applications. Mark my word, large flow rates. Now, the other option is submerged, backwashable flat sheet MBR. So we had hollow fiber MBR and we had flat sheet MBR. So the earlier when the flat sheet MBRs were designed, the challenge with flat sheet MBRs was that its packing density was not as good as hollow fiber. And as a result, you required a bigger footprint whenever you use flat sheet. Number two, they could not be backwashed, unlike hollow fibers. This too have been overcome through an innovation in flat sheet that we have done called as backflushable high flux flat sheet MBR. So the MOC is also PVDF. Yeah, one more thing. The earlier flat sheet membranes were made up of PES. So we overcome all the limitation of the earlier flat sheet against hollow fiber by developing PVDF with a pore size of 0.08 micron. It's an integrated permeate channel membrane with fully backwashable flat sheet, which was not possible in the earlier version and which was possible in hollow fiber. Double flux, because we have to overcome still its packing density is still lower than hollow fiber. So through this IPC chemistry, we improved the flux rate. So a typical flat sheet of PS was designed for something like about 20 LMH. Hollow fiber is also 20 LMH. We are now able to design the systems at 40 LMH. So we have overcome all the limitation of the earlier design while competing with hollow fiber MBR. Same PVDF configuration, backwashable now possible, and also with higher flux rate. Lower footprint and energy demand. Applications are both for industrial and municipal. The third is eco MBR. These are, polyethylene hollow fiber. I'm sorry, it's not PVDF, polyethylene hollow fiber. And as all of us know, polyethylene as chemistry is cheaper than PVDF and PS. So these are typically used for low cost MBR for, let's say, homes, that if you have a bungalow and you want to put up an MBR, or you have a farmhouse and you've got about 12 people living or 15 people living. So this is good for smaller capacities, low maintenance, low fouling, etc. So against this, now let's look at how does an MBR operate. So typically, I'll break this up into the filtration time, the air scoring time, the maintenance cleaning, and the recovery cleaning. These are the four processes which are used when you use an MBR. Whether it is a hollow fiber or there's a flat sheet, these are common for everything. So typically the filtration cycle is 9 minutes. And as I said, this is all automated. You have no other choice. Also for this particular reason, to have only fully automatic MBR. So you should actually ask everyone who's your supplier that please don't come to me with saying semi-automatic or automatic. I want a completely automated system, because without that, you'll end up into a disaster. Okay. So you have a 9 minutes of filtration cycle. Post that, you have a relaxation for about 1 minute. So these are auto control valves, which are all set to do this. Post 1 minute, once again, one goes to the filtration cycle. Then 2 to 2.5 meter cube per hour per module is the design of the air scoring, which takes place when the modules are in the relaxation phase. So look at this, that every hour, okay, you have 1 minute of air score cleaning of your membrane to remove it of all the foulants that could, if by any chance the pre-treatment is not good or there is a change in terms of your feed. So you are ensuring that your membranes remain clean through this inbuilt process. There is also maintenance clean, which is advised based upon the increase in transmembrane pressure. That's the cue for you to decide that now I should clean my membrane, because the transmembrane pressure required for filtration has gone up from 0.1, 0.2 to 0.5 bar. Of course, the membranes are very strong. They can go up to about 2 bar. But you don't want to do that, because there is also more effect of pressure and energy on the membrane, plus you're wasting energy. So you will get this on your HMI screen that the transmembrane pressure is increased. It triggers a cleaning 1 to 3 per week for 30 minutes using sodium hypochlorite, 0.1% HCl, and this is all done in situ. There is also recovery cleaning, that if your membranes are excessively fouled, or your life has crossed 3 years and 4 years, and the membranes are having a problem, or there is a problem with respect to feed, as I said, more often than not is the feed problem and inadequate pre-treatment and inadequate operation and maintenance, which results in the membrane failures. So at such times you have a recovery cleaning which is more intense. Otherwise also we recommend it once in 3 to 6 months for 6 to 8 hours using 1000 ppm chloride, as you could see. So here we are doing with 200 and 300 ppm. Now what it also tells you is your membranes must be robust to do this chlorine treatment and should not get oxidized. And that's the advantage of this PVDF new generation elements, whether it is hollow fiber or it's flat sheet, that they can tolerate high amount of chlorine. And the life of membrane depends upon the number of chlorine hours your membrane is subjected. So more you do chlorine treatment, the life reduces. So if you follow these guidelines, you can easily get a life of 3 years. And we often specify the chlorine hours that a membrane can tolerate as a barometer for life of membrane. So please, somebody says 3 to 5 years, just asking one question, boss, please tell me how many chlorine hours your membrane will be able to withstand. Because sometimes you may have to do it every month, sometimes 15 days, sometimes 1 day, depending upon the state of your MBR. And at that time, you should not get compromised with the life of the membrane. So remember this, it's a chlorine R and not the number of years absolutely, though both of them are correlated. Now let's look at some of the operational issues. Okay, now operational issues could be fluctuations of permeate flow due to air entrapment in permeate header. So one removes the entrapped air by opening the vent valve automatically. Check for leakages from joints, pipelines, and rectify the leakages by proper gluing or replacing the damaged item. The second operational, as I said, is sudden increase in TMP and obviously drop in flow. So this is due to insufficient water level in the MBR tank, and this can be resolved by maintaining the levels. So these are all automatically sensed through level transmitters. There is due to, as I explained, membrane choking, fouling. We discussed this. So check the pre-treatment and do the chemical cleaning. Turbidity in the permeate. Here we saw that one big advantage of using MBR instead of activated cells is that you get absolutely zero turbidity. This should be due to leakages from the permeate section. It could be also because the membrane pores have become big over a period of time due to life or due to improper use or due to oxidative effect, or it could be due to leakage from the permeate section. So you need to check all these things to see how the turbidity can then be controlled. Drop in MLSs. So check for incoming BOD, check for the pH, or if there are any toxic substances which is killing the biomass. If the BOD concentration is lower, add external carbon sources like jaggery, methanol, molasses to maintain the design BOD after designing, of course, after discussing with ion exchange or whoever is your technology provider. If any toxic chemical is identified, things like biocides, heavy metals, isolate them from the biological. Check the DO of the aeration tank in the MBR. If it's less than DO2, check the airflow rate and also the quality of diffusers. Okay, there could be a problem there. Increase in COD, BOD, nitrogen, and phosphorus. Check for incoming COD, MLSs, MLVS ratios, BOD, COD ratios. If COD is higher, inlet COD needs to be corrected through adequate pre-treatment or diverting the effluent having higher COD or BOD. This is sometimes not taken into the design because, after all, when you're treating a waste, I always see you're treating uncertainty. You may design the best plant with all your experience and the experience of a vendor like Ion Exchange. But when sometimes something happens in a process, what the process guys usually do is just open the valve and discharge it to the waste treatment plant. So good housekeeping and good awareness is also important. It's not only the job of utility to maintain effluent treatment plant, but also the process guy who should say that, yes, it's possible that once in a month, once in a year, once in 6 months, I'll get something off grade. And it has to go to the effluent treatment plant. In such case, through a diverter valve, divert off-spec effluent, put them into a guard tank, and then bleed them slowly with the main tank. Now, this is what we recommend in all our designs. It makes the design slightly expensive, but it improves the reliability of the whole system. So this is what you could do also here. And if the COD, BOD, nitrogen, and phosphorus in the permeate is more, maintain the design MLSs ratio about 0.05. Air fluctuations in aeration. tank, check the airline in the diffuser, rectify if there are any damages in the air diffusers, presence of undesirable particles, check for the screen. If the screen in the pre-treatment is broken and the leakages for the correct bypasses. So these are some fundamental operational issues that I am now bringing about. Having explained to you the concept so far in terms of what is MBR, its difference against ASP, where it can be placed, what are the design parameters one uses, what are the troubleshooting parameters that one considers. The proof of pudding is in eating. So let me share with you some case studies related to treating sewage and case studies treating industrial effluent with different types of membranes that we discussed, hollow fiber, flat sheet, submerged, side stream. So I'll summarize my presentation now with a couple of case studies. So this is a case study for sewage treatment. This is Navi Mumbai Municipal Corporation. It wanted to upgrade the existing STP level of treatment. So they had an SBR system just set up 5 years back. All promises were made, but it could never deliver the quality of BOD, COD, phosphorus, nitrogen required for reuse, because this water was supposed to be reused for Navi Mumbai. And that is why they put up this expensive SBR technology, which is also nothing but an activated sludge process. Okay, so but they were not getting this performance. So it was a classic case of retrofit. In order to see that the treated effluent quality is met through a retrofit. So once again, space was limiting. So MBR was chosen over here under the Amrut scheme. And in order to meet the treated sewage quality to be used by the industry and as per the CPCB norm, and to supply the treated sewage to industries for non-potable purposes. So it essentially became a tertiary treatment, but as a retrofit to the existing activated sludge process based on SBR. So we evaluated various types of options. We straight away didn't give MBR because ion exchange has all the technologies. Anaerobic, aerobic, within aerobic, MBBR, SBR, MBR. So if we recommend a technology, it's not that we have only one technology and we don't have other technology. We do this analysis very thoroughly and then decide what is the right technology which fits a requirement. So at the end of this exercise, together with NBBR, with NMMC, we decided to use MBR for this process. And we installed a full-fledged, completely automated 100 KLPD flat sheet MBR system, which is backwashable. And this we had licensed from Vito, Belgium. So the policy in my company is, though we have strong R&D, we spend nearly 2% of our revenues on R&D, employing 200 scientists. If the R&D cannot deliver, we either license or we outsource technology so that the market gets the right product and it doesn't have to wait upon the R&D taking. And it's also a big challenge to my R&D to deliver and to develop products meeting the market requirements on time. So apart from meeting discharge guideline, it also meet the NMMC's treatment objectives, including virus and bacteria-free water without chemical treatment. It was installed on time and it achieved desired objectives. And as you could see, the tank, this cream color tank are the existing SBR. And just against one section of the SBR is the whole system, which includes anoxic tank. Anoxic we required in order to reduce nitrogen and phosphorus. This is the aeration tank, and this is the MBR tank. These are the two permeate tanks. This is the CIP tanks. These are standby pumps, standby blowers in order to build up redundancy. And as you could see here, there's a big difference that we also found between SBR and MBR while doing the study, that if it's a 37.5 MLD plant, the footprint, if one selects MBR, is just 6,041, half of an SBR plus tertiary plant, less than half. Okay, this is 6,000 meters square, this is 15,000 meters square. For the same 37.5 MLD, MBR produces 375 million liters of sludge, whereas an SBR activated would produce double of it, 515. I talked to you in my presentation, the advantage of MBR is lesser sludge dewatering equipment, and also the associated operating costs involved with the dewatering. You could look at the power consumption, almost 86 into 10 raised to the power 6 kilowatt per hour annum power savings. And if one compares the life cycle cost, okay, in terms of capex, in terms of area requirement, in terms of civil, in terms of OPEX, etc., MBR in such cases would turn out to be a winner. The second example of a retrofit is HMEL. They had an existing treatment plant and they had big problem with respect to getting the right performance. And so we retrofitted a 12 MLD refinery treatment process in a very short span of 4 months during COVID. And in order to get better quality of COD, BOD, ammonical nitrogen as a feed to the downstream UFRO plant. And we solved their big problem of the biological process in less than 4 months time during COVID for a 12 MLD plant. So you could see this is how the retrofit was done. This is submerged, this is how you immerse it. And, these are immersible MBR. So at some point of time, if you want to remove them, you can just lift them through the hook by disengaging the pipes, interconnecting pipes and taking it out. And this is how, you could see when the aeration is on. And you could look at the effluent qualities that we got, less than 50, less than 2, less than, nil, no bacteria, no viruses, despite, high CODs of a refinery. Now, this is what I talk about the CapEx and the OPEX, the total life cycle cost. So what includes is the membrane operating, membrane module cost, economy of the scale using the best membrane systems, then the electromechanical equipment, energy cost, civil cost, chemical cost, put together the CapEx and the OPEX to have a lowest life cycle cost. We have also invested while doing all the membrane technology. Today the subject was MBR, but we are the largest producers of all types of MBRs, as I told you, in a state-of-art center of membrane excellence. What you see here is our membrane manufacturing facility. We make ultrafiltrations, ROs, nanofiltrations, etc. And this is the factory which is 10 kilometers away, where we assemble all the membranes into a system. So Goa is a center of membrane excellence. With this, I end my presentation. You had given me time up to 12 o'clock. I hope I have done justice to the topics as well as also to the time. Thank you very much. And I will be ready to answer some of your questions. I hope to answer all of them, but if I don't answer, I'll revert back to
you. Thank you, Mr. Popat. It was a nice presentation and a good explanation. So we'll invite the questions in brief from the participants, if any. Please share the questions so that Mr. Popat can respond.
Mr. Ajay, good morning. My name is Hardeep and I'm calling from Bharat Oman Refineries Limited, BORL, BINA.
Yes.
So thanks for this wonderful presentation. In fact, it was very good. So my question is a little different. In between in your presentation, you said that ETP unit is actually, it is receiving feed all the time and it is very, very uncertain the process people will give the ETP people anything. So you also said that there should be a diverter valve or a guard pond kind of a thing where the contaminated stream should be stored. So
yes.
Do you have some design basis, or can you guide us that
Sure.
What should be the basis for the such a storage facility?
Yes, yes. See, let me give you a practical example now. Okay. We have constructed one of the biggest zero liquid discharge plant for a refinery, which is Reliance Industries Jamnagar. Okay. Just to give one example is that, refineries can process, sweet crude, sour crude. The difference between sweet and sour, as you know, is the level of contaminants in the crude. And where does that crude go after distillation? It goes to the waste treatment plant. So if you use a sour crude, you'll have more of phenol, more of BOD, more of thiocyanate, etc. And if you process sweet crude, you'll have lesser of these values. Now, this is only with respect to the feed refineries processing, but then there are process upsets also, which would result into the parameters with feeding the waste treatment plant getting changed. So we put up sensors to measure all these key parameters at the feed line itself. So we have an online BOD, online COD, online ammonia, online thiocyanate, online nitrogen. So moment it is sensed, it would divert the effluent to a guard tank. And it would slowly bleed over a period of time to the stabilized effluent. So we do these designs. We are putting up one of the very large plant at Paradeep for treating PXPTA effluent. There, of course, it's an anaerobic as well as aerobic using MBR once again and RO system to recycle. Once again, we have the same concept there to divert off-grade PXPTA effluent. So we can work with you. I put down my email and my contact number. We are already doing operation and maintenance at your end, as you know. So you can connect with one of my guys and you can connect with us and we'll work together with you to see how we can help you on this.
Okay. Okay. My question was like that the storage facility should be how big? Should it be like...
well, I'm a very old engineer and I'm not hands-on. So it's obviously we'll calculate and we'll tell you, my guys will do a better job. Please don't ask me that 100 meter cube, what is the tank? I'll fail. I admit.
No. Okay.
Okay. You have mentioned more about the effluent treatment processes. I believe the membrane bioreactors could be used in the chemical process industry also for chemical reactions.
Yes.
Can you give some examples there and how is the success story there?
Very successful. I have given you two extreme examples, Mr. Bang. Treating refinery effluent, I would believe, is the most challenging anyone would have, because the challenge is associated with uneven BOD-COD ratios, uneven large volume of BOD-COD, large amount of contaminants. So there is nothing more challenging than a refinery effluent. And I showed you an example of HMEL, where we retrofitted with an MBR and it's functioning very, very well.
No, I thought for carrying out the chemical reactions, chemical process in the manufacturing for chemical processes, yes, or biochemical processes, yes, not the effluent treatment. Of course, you have presented. We have listened to that. I'm talking for production processes.
Oh, you mean to say to separate production contaminants? You got a production process and you want to use a membrane to separate that. Am I right?
Yeah, I mean, in chemical production processes.
Not an effluent. It's not an effluent. It's a process.
Not an effluent in the manufacturing process.
Oh yes, oh yes. Oh, so it's a different subject. But we have a very wide range of membranes to do efficient suppression, purification, and concentration. All the three. But there are different membranes. Okay, so we use them for a variety of processes. Now, this is basically ultrafiltration or nanofiltration, but very specific ultrafiltration, nanofiltration membranes, which are solvent stable and which are acid and alkali stable. One should not mix them up with water UF-NF ROs. Okay, these are UF-NF RO with respect to molecular weight cutoffs or particle size distribution. But in terms of mechanical stability, because process is different than water. Okay, it will have solvents, it can have excess of pH. So these are solvent stable, extreme acid alkali resistant membranes designed in a different way. Okay, for this process applications for purification, suppression, and concentration. Apart from this, Mr. Bang, we have now also introduced ion exchange membranes. So you had ion exchange for process suppression, purification, and filtration. It is still used as a polisher, not as a bulk. Membranes are used for bulk suppression. So now we have a combination of membrane and ion exchange. So the ion exchange chemistry is converted into a membrane, and that ion exchange membrane is used for all these three applications. So I'll discuss with you one-on-one your specific requirement and select either a membrane or an ion exchange membrane or an ion exchange process to meet this requirement.
So, if there is no more question.
Okay, Mr. Bang, does it answer your question?
Well, I was requesting you to tell some of the processes where it has been applied. If you can get some examples, like in the fermentation process where people have used it.
So for example, one of the
like even penicillin applications, people have used it. So if you can give us some process applications, that will be useful for the engineers participating.
वो बोलता है ना कि अगर आपने कोई कलाकार को गाने के लिए बुलाया है तो बोलते हैं हमें ठुमरी सुननी है. Okay, वैसे कलाकार पॉप भी गा सकता है, तो आपने मुझे एक पॉप म्यूजिक गाने के लिए कहा, तो मैं पॉप भी सुना देता हूँ आपको. Okay. So because I had prepared myself for this MBR, I thought, but I'll answer you. The widest applications that we have, I won't name people here because we have a non-disclosure, but we have commercial installations, essentially for purification of antibiotics, concentration of antibiotics. If you have an organic salt, Mr. Bhatt, for example, so you have, let's say, for example, sodium lactate, okay, any organic salt. So we have a proven and commercialized process to convert that into lactic acid and sodium hydroxide. So these are typical examples in chemics. We got at least about 100 references, okay, for suppression purifications of all these types. But again, it is not one technology. It is case specific. So generally, as I answered you, very generally, earlier people were using ion exchange processes for suppression, purification, concentration. But then, ion exchange process cannot handle large volumes of these contaminants. So if you have to do bulk, membranes will do the bulk. Like, let's take an example of RO. That if you want to desalinate water, let's say seawater, extreme example, 35,000 ppm TDS, you cannot use ion exchange process. You'll use a membrane process, you'll bring it down to 50 ppm, and then you'll polish 50 ppm with cation, anion, or a mixed bed for your boiler requirement. So that's where membranes are, and that's where ion exchange is. So earlier, ion exchange resins were used, but they had to do an extensive pre-treatment to bring down this contamination. But now you don't have to do that. You can use cleaner membrane process to do the bulk clarification, filtration, purification, and then you can polish it off with ion exchange process. Now, the third thing which I said is that this very exciting development of ion exchange membranes, which can do all these things very effectively. So in terms of history, the bulk of things was done by ion exchange for more than 50 or 100 years. In the last 20 years, membranes have replaced ion exchange process. And the third thing now that has happened in the last 10 years is ion exchange membrane process. So that's the chronology with which this happens. So there are definite answers. I don't think we cannot do anything. We can do almost everything using any of these three suppression technologies.
Yeah, this is Subhash Tandon. Do you manufacture membranes for electrochemical industries like water electrolysis, sodium chloride electrolysis, potassium chloride electrolysis, etc.?
Well, we don't manufacture them, but we have a tie with one of the world's largest membrane supplier called as Astom. Okay, Astom is Astom is nothing but a joint venture of IIChE, the world's largest membrane manufacturer, particularly for chloralkali, and Tokuyama Soda, which is the world's largest chloralkali. So we have a joint venture with them to offer these membranes for electrolysis.
Thank you.
Hello, this is Narendra Khadse from Baroda. Can you hear me, Mr. Ajay?
Yes, I can hear you, Mr. Khadse.
I have two fundamental questions. The one thing is these membranes, do they have a temperature limitation?
Yes.
Because normally most of these effluent treatment plants, they are open, and the ambient temperature conditions and variations, they will affect the performance of the membrane.
Yes.
Number two is the instrumentation, what you are saying about the automation.
Yes.
The automation word is very, very nice, but the implications of the automation under variance of the atmospheric conditions, they fail. And when the automation fails, then all trouble starts. So are these effluent treatment plants are covered or closed, recommended? And second thing is the number of trains. Suppose I need 1000 cubic meter per hour, one single train, or I should go for 500 cubic meter, 2 trains, so that when the trouble comes in, the train can be switched on for maintenance and it can be operated well.
Mr. Khadse, let me give you a very simple layman's answer to your fear about automation. Most chemical plants, refineries, for example, are all open and they are all automated, and instrumentation doesn't fail. Aircrafts are all automated, they don't fail. Our mobiles, which are used in various dirt conditions, PMI conditions, sweats, they don't fail. So I would not, I have no doubt at all that, automation leads to failure. Wrong maintenance, improper maintenance, improper design are the reasons for the failures, but not because of these things. And we have huge number of plants, large flow rates, capacities, where certainly we have not had to replace, instruments and automations. Okay, and not only me. Okay, I'm speaking on behalf of the industry. The second thing you talked about, I forgot what you said. You talked, yeah.
Temperature limitations of the RO membrane.
Yeah. So no, we're not talking of RO. We are talking of MBR right now. Okay.
Yeah.
So they are submerged membranes. Okay, and they are within within water. And even if your ambient temperature is 45 to 50 degrees, your water temperature will not go beyond 30, 32. But you are right that temperature plays an important part, not essentially from the membrane life, but with respect to the process. The biological process is greatly influenced by the temperature. The membrane process is also greatly influenced by temperature. So for the process related consistency, we need to have temperature control. Not that membranes cannot go beyond 45 because the ambient temperature is 32, but I don't want to run at 32. I want to run at 30 for efficient performance of my biological system and my RO system. So we'll have temperature controllers, heat exchangers, wherever a process requires efficient control of temperature and efficient process management. So that's my second question. Third question you asked about capacity. So these are all modular capacities. Okay. So as I said that anytime we develop a technology, then next thing my company does is to standardize it and we modularize it. And that is why we are not very popular with consultants, because a consultant would like to spec in everything. I'm sorry if there are any consultants here. Okay. But we give a standard design, which is pre-engineered, pre-designed. It saves cost, time, and so it's available in a modular form, Mr. Khatz. UF, RO, MBR, everything is available in a modular form. Right from your home RO, which is 5 liter an hour, to a desalination plant, which is 100 mld per day. They're all available in standard modules.
And what is the inventory level? What you recommend? The inventory of the membrane at the
zero, because we supply membranes ex stock from Goa.
Okay, thank you, Mr. Ajay.
Hello, sir. Can you hear me, sir? Hello. Hello, can you hear me, sir?
Hello.
Sir, actually, I am a research scholar from IIT Roorkee. I am working on membranes. So I want to know that is there any fouling issue regarding the operation? If yes, then how will you remove this? And what is the life of the membrane?
I think I don't know if you joined my presentation. Did you attend my presentation right from the beginning?
Yes, sir.
So there was a slide where I talked about 9 minutes of service cycle, 1 minute of relaxation where air scoring is done to remove all foulants. 2 to 3 times cleaning with 100 ppm chloride, hypochlorite solution to clean all the foulants, including biological, chemical, and once in 3 to 6 months, rigorous cleaning of the membranes to remove all the foulants.
But sir, any deposition over the membrane, then how will remove this?
Through this cleaning mechanism. Not about the, through this cleaning mechanism.
Okay. And sir, what is the life of the membrane?
I also talked about that, saying that we don't talk of life of membranes. We talk about ppm chlorine tolerance of the membrane, because you're going to be cleaning membranes with chloride ions, chloride Rs. But if I have to just convert it into simple thing, anywhere between 3 to 5 years, depending upon how you use the membranes. Okay, so if it's a good design plant, if it's operated and maintained well, as the right level of service provider, easily 5 years. Okay, I'll stick my neck out to give such people 5 years life.
Okay, thank you, sir.
Hello, can you hear me? Can you hear me?
Hello. Hello. I think someone is trying to speak.
Yeah.
Mr. Krishna, yes.
Yes, I have put a question to you. of course it is. I think it is MBR is a misnomer because there is no reaction taking place. It's only a separation. You are only separating, removing or substituting this membrane system to clarify. I wonder what is MBR in this?
Well, you explained it very simply as what I also try to explain, the difference between activated sludge process. So one of the things is that in a very simple language, is actually the membranes are doing the job of a clarifier, but more efficiently.
Exactly.
But that's not all. That's not all. I also said that the design limitation of activated sludge processes with clarifier is the ppm level of suspended solids that a clarifier can tolerate. Okay. So that's about 2000 or 3000 ppm. So if your biomass which goes out of your aeration tank is more than 2000 or 3000, which often it is because you have got flocculated mass, your design would be limited by the clarifier. But since now in a MBR you can go up to 8 or 12,000, there's no longer a limitation. So that's how it reduces the footprint. But as I said, that
there is a reaction taking place. That's what I'm asking.
There is no reaction. The reaction only is biological reaction that takes place where the COD, BOD, and organic contaminants is a food for the bacteria, like human beings. And like human beings, bacteria also require oxygen in aerobic process. And the food is destructed by the bacteria. And the bacteria will then produce,
and that is taking place in the aeration.
It takes in the aeration tank. You're right.
Yeah. So MBR is the membrane is basically separating a very efficient separation of the.
Yes, in a simple way, I would say yes, I agree, and that's what I said.
Then the second question is, how elaborate treatment is required, pre-treatment is required for making the effluent suitable for the process.
Same as any biological process. There's nothing different for MBR. Same, because
you will have to go for extensive filtrations, I suppose.
No. Nothing. I mean, if this is something which a guy who does not have an MBR will say, कि अगर MBR लगाओगे तो automation बहुत लगेगा, MBR लगाओगे तो pre-treatment बहुत बढ़ेगा. Nothing like that. Nothing. Understand that it's a plain aerobic activated sludge process. So what sort of pre-treatment is required for an aerobic process, which includes MBR as well as ASP and SBR and MBBR and everything? Okay, is something which the bacteria cannot tolerate, because bacteria are the ones who are working on the effluent. So what is it that the bacteria cannot tolerate? They cannot tolerate high temperatures. Somebody said that. Okay. Number two, they cannot tolerate extremes of pH. They cannot tolerate sometimes high salinity. They cannot tolerate certainly toxic compounds, antibiotics, for example. Bacteria, we take antibiotics when our stomach is upset. So bacteria cannot tolerate all those things. Okay, heavy metals, oil and grease, for example. So if your effluent has all these contaminants, or you have a knowledge that your effluent is likely to have these contaminants, build your pre-treatment accordingly.
I accept it. Good. One thing is, where does this hypochlorite backwash, etc., where does it go, and does it not create an additional effluent problem?
No, it doesn't, because the treatment, as you saw, is just about a few minutes.
Yeah, but where does it go? Where does it go?
Well, it oxidizes, it cleans it. Like any oxidant, it gets oxidizes, and there's no residue left. It's consumed while cleaning.
Okay.
Hello, sir.
It's consumption. It's consumed.
Hello, sir. This is Vinod from Jubilant Nira.
Yes.
Here we are maintaining the MLS level is around 8,000 to 12,000, which is far more than our conventional system.
In a MBR?
Yes. Okay. We are maintaining more MLS level. No?
Is it a flat sheet or a hollow fiber?
No. In MBR, we are maintaining the MLS level is 8,000 to 12,000.
So is it a flat sheet or a hollow fiber MBR?
Hollow fiber.
And submerged or external?
But we are maintaining here in MBR system, any system, we are maintaining more MLS level than our conventional system, right?
Correct.
But here is any choking problem, because in other effluent treatment plant, RO plant, okay, we are maintaining this suspended solid level is less than 2,000. Then here is no possibility of membrane choking.
No, even in RO 2000, in RO also 2000 is not accepted.
Okay.
RO, any RO membrane, we are the biggest, or you can check up with anybody else also, open up a spec sheet of membrane. They will say suspended solid nil, turbidity nil,
Yes.
BOD nil, COD
Yeah.
nil, chlorine nil. Okay. So I don't accept that RO membrane can accept 2000. If it is accepting 2000, you are using it as an expensive filter. Because you're cleaning it more often, producing more using more chemicals. So 2000 is not even accepted for RO. In fact, its tolerance to accept suspended solid is the least, because the pore size is the tightest.
Yes.
And that is why in the pre-treatment, one uses ultrafiltration.
Right.
To remove suspended solids, to remove colloids, to remove turbidity. But that too not 2000 ppm.
But
Okay.
here we are using this membrane filter system in high MLSS level. This
Sorry?
MBR technology. This MBR technology
when
we
you're
are using at high MLSS level.
No, when you are saying we are using, means it's your plant, or you're talking about
No,
my presentation?
general MBR technology.
Uh-huh.
MLSS level maintain is around
Yes.
more.
Yeah, because it is effectively filtering. No, you can go up to about 8,000. You can go up to concentration of something like about 1%. Okay, and it's filtering. And as I said, it's ultrafiltration. So the size of this MLSS is bigger than the pore size of the membrane, and that's why it doesn't come out of the membrane. So it filters, and that's how it concentrates. Okay, if it was RO, for example, it would not have been possible. It would have fouled up the RO. Okay, and that is why you saw your question is very, very scientific, I must say, and very practical, because you are right, though you have not asked, but I know what you are trying to say, and thanks for giving this angle. Because see, more and more the biomass is there on the surface of the membrane.
Right.
The biomass can also accumulate across the surface area of the membrane. What will happen? Transmembrane pressure will go up. Okay. Yeah. You will then initiate, what you will do? You'll initiate cleaning.
Yeah, right.
But in my presentation, I showed that you are not even waiting for TMP. Your MBR process says that every hour, there's a 10-second air scouring. Air scouring means mechanical cleaning. Okay. So if you are cleaning mechanically something which is trying to adhere, before that it is getting adhered or solidified, you are cleaning it away. But still something will be there. आज हम कुछ खाना खाते हैं, टेबल पे गिरता है, हमने क्विकली साफ कर दिया, लेकिन दाग रहता है. फिर हम क्या करते हैं, उसके पे वो केमिकल डालते हैं, क्लीनर. So that's what you do, the chemical cleaning, in order to cleanse the surface. Okay, once in a week, twice in a week, depending on that. And then हम क्या करते हैं, 3 to 6 months में we take a extended cleaning. Okay, these are all maintenance cleaning also, not necessary कि आपका TMP बढ़ गया. You're taking care, okay, through such things.
Forward following.
Yeah.
Thank you.
Okay, Vinodji.
Yeah. If there are no more questions.
Excuse me, can I ask? I'm Supriya Sapre from Bharat Petroleum Mumbai Refinery. Sure. We have a plant which is powdered activated carbon technology based, and if there's a retrofit we want to do here, will MBR work, or will it require some?
You want to do retrofit for what purpose, Supriya?
Basically, we want to have some capacity enhancement little bit, and also for meeting, because the refinery unit configurations have changed, and that is why the effluent quality also has changed. So we are not meeting the minimum national standards. So for COD BOD reduction as well as little bit capacity enhancement, those are the two purposes for retrofit.
Okay, I get your question. So it was exactly the case of HMEL. Okay, they had an existing plant and it was not performing, and the space was limited. I'm sure in your case, because you are in Mahul, again the space would be limited, because everywhere, the least space is always given to effluent treatment plant, even while designing itself. Okay, so one of the biggest challenges that we always face, apart from price, okay, and commercial terms, is space nahi hai. Okay, so I'm sure you will be having this issue also.
Yes, sir.
So MBR becomes a good option to essentially improve the quality of treated effluent, okay, and making it compliant with the newer standards, okay, beyond MINAS standards in refinery, and making it suitable as a feed to downstream membrane processes to recycle the water. So that is one answer. Second answer is, we'll have to really look into your case, because see, if you have the PACT process of Zimpro, I guess it's Zimpro, right?
Yes.
So sometimes what happens is that there is a carbon carryover, And if your clarifier is not doing a good settling, this carbon carryover can go and sit on the MBR membrane. MBR membrane is not designed to take carbon as a suspended load. It's designed to take bacteria as a suspended load, MLSs and MLVSs. So if there is a carryover, there will be a problem with MBR, and that has to be first arrested. So once that is arrested, and assuming there is no carbon carryover, you want to improve the quality, exactly like the NMMC plant for municipal, exactly like HMEL. I gave a 2 example of retrofit itself. Why I took these 2 examples among several that we have is because always space is a constraint, and always improvement of quality is the need, and that's where MBR fits very well as compared to all other biological processes. So my answer to you, based on this very brief discussion and the clarity that you gave, that yes, you could look at MBR as an option.
Thank you. Thank you.
Where are you located, Supriya ji?
In Mumbai, refinery itself, Mahul.
Okay, so we could fix up a meeting, okay? And
Yes, certainly.
we could have a dialogue on that. I've already posted my email and mobile over there, so we can always engage with you.
Yeah, sure. We'll be in touch.
Any more questions, please? So now, if no more questions, I think people have been a lot involved in participating in the lecture. So I'll request the Joint Secretary IIChE NRC, Dr. Dheeraj Garg, to please propose the vote of thanks to the speaker and to the participants. Professor Dheeraj, please.
Thank you, Srivastava-ji. Namaskar, everyone. It was a wonderful talk by Mr. Ajay on membrane bioreactor technology. In his talk, he talked about the aerobic biological treatment of organic sludge, especially the activated sludge system, in which the biological solids are used over and over again. He discussed about its design and parameter, the membrane bioreactor technology, which combines actually filtration with APS, where the membrane is basically the use for separation of organic and suspended solid particles. I also discussed that several is offered by MBR in terms of both quantity and quality, thus improving the process intensification. He also discussed operating parameters of membrane operation, like transmembrane pressure, specific flux, permeability. Also discussed the basic design guidelines for MBR. He mentioned about several types of MBR like submergent or side stream. He gave some points about the innovation, their innovation on the backwashable flat sheet MBR from the previous limitation. And in the end, he discussed some successful case studies like one MBR installed in MMC and another in HMEL. Through his talk, he clearly elaborated great potential of MBR. I would like to extend my thanks on behalf of IIChE NRC to Mr. Ajay for this wonderful talk, and also to all the attendees for making this talk successful. I would like to thank everyone for joining in large numbers, taking your time out of your busy schedule. Thanks also for making it a lively talk through great questions and equally apt response from Mr. Ajay. Hope it will help and promote students, faculty members, and people from industry to have new ideas, collaborations, etc. in this area. Now, I would like to hand over back to C.P. Srivastava. Thank you, everyone.
Thank you.
Thank you very much. And as I have written in my chat box, that it was very nice speaking to all of you, and also for a very interesting interaction and queries. And thank you, IIChE, particularly Mr. Bang, okay, who wrote to me personally, and I immediately accepted because I love to share all my experiences. And thank you for giving me this opportunity, because it was very nice for me to be with you this morning.
Thank you.
Thank you, Mr. Popat, for your nice lecture. And once again, thank everybody. So we conclude this session of today, and we all and our IIChE NRC members meet again next month in some other good talk by some another good distinguished leaders. Thank you all.
I have just one request, Mr.
Sure.
Srivastav. While you have invited me as a speaker, next time please do invite me also as a participant.
Sure. We will.
I'm not a chemical engineer, okay,
Sure.
and I'm not a member of IIChE North.
Doesn't
But I
matter.
would still like to learn from, because today it's my turn to share knowledge and experience. Tomorrow it will be my turn to listen to one of you, speaking. So please give us that opportunity, not only me, but also a lot of my team members. So please do extend, it's like ion exchange, it's a barter.
We will keep in mind, you may not be a chemical engineer, but your experience in chemical industries and process industries is very valuable.
Thank you, sir.
Share that and we will keep in mind.
Yeah, thank you very much.
Mr. Popat will keep your contact details with us forever, and we'll be contacting you every time we organize the program.
Yeah, please. Thank you very much. Yeah.
So, Luthra Sahab, we conclude the meeting for today.
Yeah, sure, we can do it.
Okay.
Thank you very much once again on behalf of NRC, and nice meeting all of you, and a very proactive session for last many times, and there is a good participation also. Thank you very much.